In the first half, we talked about global warming and the role of soils as a solution to stabilize CO2 at safe levels. In the second half, I'm going to be talking about marine ecosystem restoration. And we concluded the solution to the global climate change problem lay in the land, not in the sea. But the sea, nevertheless, has been very badly affected by the human impacts, and we need to restore our ecosystems. Very simply, the standard strategy of setting up marine protected areas and claiming that that will solve all fisheries and coral reef issues has not worked, because it only works where you're protecting prime quality habitat, and that's disappeared almost every place. So if we don't restore the quality of the habitat to have the capacity to hold large numbers of fish, we're not going to have our fisheries in the future, and the corals aren't going to come back. So active restoration has to be a key part of that. And as I mentioned earlier, coral reefs are the most threatened of all ecosystems by climate change. We've lost most of the corals already, and therefore we're in a very critical situation now. Right now it's very warm. We're getting into an El Nino year. Right now all the corals in Cuba, Panama, Florida, and Hawaii are badly bleached from high temperatures. They're now cooling down in all those places and recovering, but Indonesia's heating up, and we could have very bad bleaching starting in Indonesia in a couple of weeks, which is catastrophic because Indonesia has the world's largest area of coral reefs and by far the highest biodiversity. The biggest range of corals and fishes and clams and worms and everything are in Indonesia. So that's of critical importance. So we're going to have to grow back our ecosystems if we want to maintain the services they provide, particularly fisheries, tourism, and beaches. And I want to show now how we have developed technology to do that of a very different kind than what we do on land. On land, what we do is we restore the fertility of the soil by adding the missing nutrients and elements plants need in a way that they can recycle them naturally and be highly productive. In the ocean, we're going to do something very different, because in the ocean, all the elements are present in excess, except for nitrogen and phosphorus. Those are the only ones that are limiting. And coral reefs are not only the most temperature-sensitive ecosystem, but also the most nutrient-sensitive of the ecosystem. So if you add any nutrients to coral reef, you kill it. It gets overgrown by weedy algae. So coral reefs can't take any more nutrients or from land-based source of pollution anymore. They can take more global warming from CO2. So we have to do something very different with regard to coral reefs and marine ecosystem. That is basically to supply them with biochemical energy, the energy for growth and resisting stress. And I will show you how we do that now. This is what we call Biorock material. This is a material that's grown on a steel framework in the sea, in this case mostly pieces from the Maldives. And it's a bar of steel the size of my finger, and we apply a low voltage direct current to that. It's completely safe, a few volts, a few amps, and what that does is two things. One, it completely prevents all rusting of the steel. It does not rust at all. And then secondly, it causes limestone minerals, which are the rocks that coral reefs are made from, and many white sand on coral reef islands are made from. That limestone calcium carbonate then precipitates on top of the steel and grows over it, and we wind up trying to grow it typically between 1 to 2 centimeters per year. And if we do that slowly, we get material that's 3 times harder than ordinary concrete in terms of load-bearing strength. So we can grow this in the sea. It's cheaper than concrete in most places, and we can grow it in any size or shape in the ocean. This was invented by Wolf Hilberts, an architect in the 1970s, produced building materials from the sea, and this is the only marine construction material that gets stronger with age and is growing and self-repairing. And I'll show that in a few moments. It also has remarkable biological properties as well as physical and chemical properties. This is an example of a Biorock structure here that was hit by a boat after being 12 years in the sea, and the boat smashed in, and you can see it broke off. This is the white limestone material that grew over the steel bar, about the size of my finger, and that steel that had been in the ocean for 12 years had no rusting on it at all after 12 years. And all the white limestone material broke off, and what happened then in the next year is we applied a very slow trickle current to it, it healed right back and grew itself. So it grew new limestone back over the steel and filled in the gap in the space that was damaged. So this is a material that repairs itself if it's damaged by storms. It gets stronger with age. Now, in the area around that project in Bali, when we began, there was about 1% live coral. All the corals had died from high temperatures. They'd bleached and died, and they'd also been killed by use of bombs and poisons by fishermen. to catch fish. And so when we laid down the electrical cables for our projects, you can see here, there was essentially nothing left alive on the bottom. It was barren of life. There were no fish. There was just nothing to see there. This is the same place 10 years later. It's now essentially 100% covered with live corals of all sorts. And by putting in the electrical field, we've greatly stimulated the settlement of all forms of corals and all forms of marine life and fish. And you'll see it much better in video than I can show with a photograph, but it's just quite spectacular how the whole ecosystem has come back because of our ability to grow corals using the electrical field. This is a 4-year-old reef in Bali, and when we began, this was bare rubble and sand. There was nothing there. There were no fish here. And after 4 years, we've just got these huge clouds of fish completely covered with corals that are growing very densely branched and proliferating like mad in all directions. And this has not only restored the reef of this entire village, it's restored their fisheries because it's restored the fisheries populations that then have spread out and populated the surrounding areas. So the fishermen say they're now catching much more fish because of this project than they were before, and they're very strong admirers of it. Well, this shows some of the data we get from this, and this shows the recruitment, the settlement of baby corals on the limestone. Baby corals are looking for clean limestone to settle on. They won't settle on rubber tires or concrete or plastic trash or sediments or algae. They're looking for clean limestone. And so we get settlement rates hundreds of times higher than is typically found in the field. So they're attracted by the electrical field. It's not just corals, sponges, all forms of marine life settle in very great densities. And that's because they actually have a little electric charge, a little microscopic larvae. One end is positively charged and one end is negatively charged, and they use that to find the bottom. And so we're attracting them in huge amounts. The corals and oysters and everything that we grow many times faster than the genetically identical specimen grown outside of the electrical field. We get typically 3 to 5 times faster growth rate, in some cases 10 times faster growth rate. Sponges, corals, oysters, almost everything we do grows faster. They have much higher survival under conditions of stress too. So our corals are not only growing faster, they're stronger. And this is survival for conditions of extreme high temperatures, sedimentation, or pollution. So, and this is, again, corals, oysters, and other organisms. So we get much higher survival. So this means we can keep coral reefs and oyster reefs and other marine ecosystems alive where they would die under conditions of extreme stress. And we can grow them back in just a few years in places where there's no natural recovery. And that's quite unique about the Biorock technology that we've developed. And the reason it does it is it acts at a very, very fundamental level. What the Biorock process does is it's creating the ideal biophysical conditions that all forms of life use to make their biochemical energy. You know, all forms of life do the same thing. There's about 1/10 of a volt electrical difference between the outside of the cell and the inside of the cell. And that voltage difference causes a small electrical current to flow through the membranes of all cells. And we have the enzymes that grow that tap that electrical current to make our biochemical energy. We have to spend about 1/3 or 1/2 of our biochemical energy pumping currents back across that membrane to maintain the voltage difference, because if that voltage difference collapses, we die. All forms of life die. I mean, it's absolutely critically dependent on that. And in effect, what we're doing is we're creating conditions that they're getting free energy, a small trickle charge of free energy. So they have more ATP. And this graph here shows how over a wide range of current, you get higher ATP formation in cells than at low current, you don't get any, in too high levels you don't, but there's a wide range in which you do. So it's a very fundamental biological benefit that we can stimulate all organisms in all habitats and grow fisheries back, for instance. Now we can also grow beaches. Here's an example in the Maldives, the lowest country in the world. Every single island in the Maldives is washing away. They have a critical erosion problem. And in this island, their beach had completely disappeared, been washed away. It's a tourist island. They're desperately piling sandbags, but the buildings and the trees were falling into the sea, and they were desperately trying to save it. What we did here is we grew a Biorock reef right in front of this beach, in the sea, right in front of this eroding beach. And we grew a reef and transplanted corals onto it. And then in about 2 years, we grew a new beach behind that reef. 50 feet wide or 15 meters, grew in about 2 to 3 years. When we began, this building was falling into the sea. The management of the hotel said there was nothing that they could do to save it. They were going to have to tear the building down and abandon it because it was impossible to save. And we grew the new beach right in front of it, just in a couple of years. And it's been stable ever since then. And so, and that happened, I say, very rapidly. Here is the new beach we grew. The first picture of the sandbags was there, and that last picture was taken here. And the dark line in front is the Biorock Reef. And that whole beach we grew back using about 1 air conditioner worth of electricity. So in order to grow back that whole beach. And furthermore, our Biorock Reef there had 50 times or 5,000% higher survival of the corals after the 1998 bleaching event. The natural reef had more than 99% of their corals die from high temperatures in 1998, and most of our corals survived. So all the fish migrated out of the dead reef into the Biorock Reef, and it made it a huge ecotourism attraction, as well as growing back the beach for this hotel. So we can do this. We can provide the electricity and many different sources. We can use solar panels, we use windmills, we're using wave energy generators now, and we're using tidal energy, ocean current generators, so we can make the power directly from ocean energy at the site. And in principle, we can grow back whole islands this way and restore beaches. Every tropical beach in the world is a serious erosion problem with global sea level rise, and because the reefs in front of them have been killed by global temperature rise. So this is the new reef we grew in front of that beach, and this is 15 years later after we grew it. And when we grew that reef, there was no sand there. It was bare rock, and the sand is piled up in front of it and behind the reef, and grew this beach. This has been stable for 15 years. The Asian tsunami in 2004 passed right over this island, didn't damage our beach. In fact, our Maldivian colleague was washed off the island by the tsunami, and he had to swim back. But the beach and the reef was not affected. So this has been extremely stable, and as far as we know, this is the only case in the world of a case where a beach has been naturally grown back by growing a reef in front of it. Seawalls don't work. Seawalls cause increased erosion until they collapse and fall down, which is inevitable. So this is a new way for growing dynamic living resources that provide fisheries and shore protection and tourism, and can be powered by wave energy generators. This is a prototype wave energy generator that we used in Bali to power a small artificial reef. And in this particular case, it makes up to 2 kilowatts of energy in about a 1 square meter size. So there's enormous potential for eroding coastlines to be grown back using the wave energy of the waves right in front of them to grow back coral reefs and oyster reefs and seagrasses and salt marshes. And this is an example showing how the prototype works. Now, one reason this is very important is that, as I mentioned earlier, marine wetlands, mangroves, seagrasses, and salt marshes have about 1/4 of all the soil carbon in the world. We've destroyed most of these ecosystems. We're burning off their carbon. But if we restore them, we can store carbon very quickly, because these peat sediments in these ecosystems are almost pure organic matter. And the Biorock method works for seagrasses and salt marshes too. We're able to greatly expand their growth. We're able to grow them under conditions they normally can't grow at all. And so this is probably going to be the fastest and most cost-effective way of storing carbon in the ground quickly in order to get rid of excess CO2. And so we have to start restoring these ecosystems extensively. Here's an example of a Biorock salt marsh in New York City. It's powered by a solar panel in the background. This is a Superfund waste site here. It's an extremely polluted site, and there we're growing it using solar panels to grow salt marsh very tall in an area that it wouldn't normally grow. And we're able to grow it lower than the lower limit in the intertidal, so we can actually expand these things seaward because we get such prolific root growth of the salt marsh. This is seagrasses in the Mediterranean in Italy, and here we're growing the seagrasses on a Biorock frame, and we're growing it on bare rock. Normally the roots can't grow in bare rock, they have to be in sediments, but here we grew seagrass, and we've got a whole community of mussels and oysters and fish and all sorts of organisms living in them, and so we're able to restore these ecosystems in places other people simply can't. This is a seagrass bed that we're restoring in the Bahamas. We have other projects in Panama too. And here is a Biorock mesh, and the seagrass has just grown incredibly tall all around and through it, and it's packed full of fish. You can't even see through it because there's so many fish inside of it. So we're able to restore fish, and the corals are growing great on it too, although you don't see it on this picture. So we have now the techniques now to grow back any marine ecosystem and create habitat for fish, whether it's a coral reef, an oyster reef, a seagrass, a salt marsh, or a mangrove. And this is something we have to do a great deal in the future. We call this geotherapy, and without large-scale restoration of degraded ecosystems, without large-scale putting carbon in the soil, without restoring the natural capacity of the biosphere to regulate our environment, which is what we call geotherapy, restoration of the natural mechanisms of our life support system, we can't solve our global climate change problem. Geotherapy is not geoengineering. Geoengineering are expensive, unproven methods that are ruinously costly and probably have worse side effects than the problems they purport to solve. We're talking here about restoring nature's capacity to heal itself. Thank you.